Hopefully you viewed the short video that I asked you to view. Remember in previous class that we have a gas that's undergoing an adiabatic expansion, or in state 3. Between state 2 and state 3, the gas undergoes an adiabatic expansion, and we have original 0.5 liters at 300 Kelvin. We raise that to a temperature that will raise the water in the column by 1 meter, so the pressure goes up to 110 kilopascals, and then we heat the gas until 0.6 liters of water has 0.06 liters of water, 60 milliliters of water has been forced out. So we have a potential energy increase, etc. So just to reframe the problem, we were calculating the work done in the adiabatic expansion, and we kind of ran out of time. So rather than running over, I ask you to view the video. Here's what I put on that video. Okay, so we have PV to the gamma is constant. Gamma is 1.4. So we have P2V2 to the 1.4 being one value of P2V2 to the 1.4. PV to the 1.4. Any other PV to the 1.4 during the adiabatic expansion is going to have to equal that. So during the adiabatic expansion, the pressure is P2V2 to the 1.4 divided by V to the 1.4. Okay? Now, P2 was 110 kilopascals, V2 was 0.56 liters. We'll use that shortly, but we're going to keep this as P2V2 to the 1.4 right now, just to keep the notation sort of compact. And so what we get is P2V2 to the 1.4. Okay, to get the work, the integral of PdV is then the integral of P2V2 to the 1.4 divided by V to the 1.4. The P2V2 to the 1.4 comes out of the integral. The integral goes from 0.56 to 0.6 liters. We got dV over V to the 1.4. Inside the integral, we do the integration. Antiderivative of V to the 1.4 is 2.5 V to the negative 0.4. And very straightforward. Just think that one through. Just ask yourself, what's the integral of V to the negative 1.4, essentially. And that's evaluated between the limits. We bring that up here. We get negative P2V2 to the 1.4 times the 2.5 times V3 to the negative 0.4 minus V2 to the negative 0.4. V3 being your 0.6 liters, V2 being your 0.56 liters. And that comes out to 4.1 joules. Just plugging in the V3 and the V2, we get 0.034 liters to the negative 1.4 out of these numbers. And the P2V2 to the 1.4 is going to be 50 kilopascals times liters to the 1.4. When you multiply liters to the 1.4 by liters to the negative 0.4, you get liters. You get the kilopascals here. Kilopascals times liters is joules. So this calculation comes out in joules. And we got the 50 kilopascal liters to the 1.4 just from the fact that P2 is 0.56 liters and V2 0.56 liters and P2 is 100 kilopascals. We then calculated T3. T3 is just this, the etc. Well, we carry that out here. P3 over P2 was 100 kilopascals over 110 kilopascals. That's about 0.91. This is 0.6 liters over 0.56 liters. I estimated that as 1.07. Turns out it's 1.06. I'm sorry, I estimated 1.06. It's 1.07. Multiplying that by T2 gives us T3. And of course, T2 is 370, and I estimated 358. It's actually 360. If we then use that 360, we go from 370 to 360, a decrease of 10 Celsius. Calculate the change in internal energy. That's going to be your number of moles, which is 0.02. Times 5 halves R, which is 21 joules per mole Kelvin, times your negative 10 Kelvin, gives us negative 4.2 joules. Now that's very close to being equal and opposite to the 4.1 joules, the only difference being round off error. So now we have confirmed that the change in energy, the delta Q23 has to be 0 because it's an adiabatic expansion. No heat energy crosses into the system or leaves the system. And from this it follows that delta U23 and delta W23 have to be equal and opposite. From our calculations, we've confirmed that independently, and this confirms just what we know that we should find.